So hello, welcome everybody for today's webinar on Bind9 memory management. So again, we have a fully packed webinar, and this time I have really thanked the team at IC, especially Kathy, Andre, and Petra, for all their good information and insight they gave me on this topic. Without them, I wouldn't be able to talk about Bind9 memory management. So we are talking about what has changed between the older versions, Bind9 11 and older, and Bind9 16 and the current up-to-date version, which is 9.18. We also look in configuration options that influences the memory usage of a bind resolver and a bind authoritative server. We take a look at memory management in Unix and Linux systems in general, and how we could measure memory consumption of a Bind9 process, and what is available in Linux operating systems to restrict the memory usage of a process, especially a Bind9 process. So if you run bind in a larger scale, that is not only for yourself in your home office, but maybe for a few thousands or more users, you might have seen that the memory usage of bind has changed over the recent versions. The reason for that is that bind is evolving. After 20 years, some parts of the code base need an update or need to be replaced. 20 years ago, the world was different, and the operating system and hardware environment was different. Today, we have multi-core systems, we have non-uniform memory access machines, we have new CPU architectures, and also the operating system APIs are today more standardized than they have been 20 years ago. So the team at ISC is replacing platform-specific code with standard libraries, which are battle-tested and much more optimized for modern operating systems and modern hardware environments than the older code. And that happened in Bind 9.16, where parts of the network code had been replaced with a modern version. So these modern networking code perform better on multi-core systems. It allows for faster TCP connection, and it was a requirement to implement DNS over TLS and DNS over HTTPS. However, not everything in the network code had been replaced in 9.16. The functions that were processing incoming requests were running the new code, but the functions that were sending the requests out, for example, on a DNS resolver, sending data or requests out to the authoritative servers, that was still using the old code. And that resulted in higher memory usage because both networking parts used their own memory management. And that was a different management, so they used different regions. In 9.18, the old code has been completely removed, and now incoming and outgoing requests are done with the new code. So the memory usage is back to the same level as we see before 9.16. But the performance impact, the better performance has stayed, which is good. So here we see a graph on the memory usage of different bind versions. The blue line at the bottom, that is the memory usage of bind 9.11. And then the orange line, which is on the top, that is 9.16. And you see that the memory usage of 9.16 is almost double the one that was in 9.11. The red and the green line are the latest versions, where green is the current latest version of bind 9.18, and red is the current development version. And we see, despite a little bump at the beginning, they are very similar to the old code, to bind 911. They use a little bit more memory, but not as much as 916. So if you have seen higher memory usage with 916, switching over to 918 might solve that problem. This graph shows the performance improvements between the versions. Lines that are more to the left show lower latency. That means faster request answers towards the clients. So here we see the blue line, which is bind 911, being the slowest one. Then there's 916, which is a little bit better, and 918 and the latest development version showing the best performance in the comparison of these four versions. And this is with a cold cache. So the DNS resolver has just been restarted and is then being hammered by a benchmark system. It even looks better with a warm cache, where both 916 and 918 and the development branch are much better than the older 911, especially when it comes to more longer running requests. So why is that? And how can we really measure the memory usage of a bind system? Because not all bind installations are the same, and some, depending on the operating system and also depending on the hardware, show different characteristics in how the memory is being used. To understand how we can measure the memory, let's talk a little bit about how memory is managed in a Unix system. The memory that applications use can come from different sources. They can come from real memory, which is the random access memory. And we can have virtual memory, which is memory that is backed by a storage device, which is often called the swap space. Besides the virtual memory and the real memory, we have anonymous memory and named memory. Now, named here has nothing to do with the bind process. Named here means it has a name. And the name is the file name on disk. Named memory is coming from some kind of files on a storage device, which usually is a hard drive. So that can be the application binary itself, the program that is loaded into memory. It can be dynamic link libraries, which are on a Unix system or Linux systems, are the files that end in .so for shared object. And it can be memory mapped files, which are files that are opened on disk and then loaded or discarded from memory under control of the operating system and not of the application. The applications are things that everything is in memory, and the operating system loads and discards these memory pages on demand. This named memory will never be stored in the paging file or in the swap file, because the data can always be reloaded from disk, from the application binary itself, or from the other files. So if the memory situation is tight, the operating system just throws out these memory pages and loads them on demand back from the files. Anonymous memory, which is usually the heap or the stack of an application, is not backed by a file. So because we don't have a file to load that data from, it needs to be swapped out, written to a swap device before the memory can be freed to be used by other applications. When an application requests memory from the operating system, that memory is added to the pool of committed memory. But committed memory is not allocated immediately. Basically, if an application requests memory from the operating system, in case of Linux, the operating system will always give the memory to the application without really looking whether that memory is available in the system. So memory allocations always succeed, mostly always succeed. And then the operating system really physically allocates the memory on its first use. So when the application tries to read or write into a memory page that it has allocated before, and that memory page is not available in the system, something that is called a page fault occurs, and that page fault will trigger the operating system to free the memory and assign that memory to the application. Because of that, we have to differentiate two different types of memory that we can see. First is the virtual memory size, which is not the real memory usage, but the memory requested and committed to that application. And the resident memory size, which is the amount of memory that is really allocated and currently in the random access memory in the RAM. So that is the process code, the binary running, all the libraries being loaded, and the heap and the stack. That means that Linux and also other Unix systems will overcommit memory. So they will allocate more memory to applications than there's physical memory in the system. And also they might allocate more memory than there is physical memory and swap storage together. And that's possible because most applications don't really use all the memory they request from the operating system. However, sometimes a situation occurs that an application really wants to use all the memory it has been allocated, and then the real memory can become very tight. In this situation, something called the out-of-memory killer, which is a process within the Linux kernel, will try to identify an application that is using A, too much memory, and B, has not been active lately, and it will kill that process out of memory. So it will throw out that process the hard way. On modern systems that run the systemd init process, there are two out-of-memory killers. There's one from systemd, which is called systemd OOMD, and there's another one in the Linux kernel. If you run a dedicated DNS server, meaning a server that is only a DNS server and nothing else, it's probably best to disable the systemd's out-of-memory killer and also to disable memory overcommit. We can disable memory overcommit by writing the value 2 into the proc.sys VM overcommit memory file. That will disable overcommit memory in the current operating system session. And if we want to make that persistent, we have to write some kind of a start script that writes the value 2 into that file on startup. Whenever you disable overcommit, you should make sure that your machine have plenty of physical RAM and also having a paging device. Having plenty physical RAM does not replace the requirement to having a paging device. It's always good to have a swap space, to have a swap device, even if you have enough physical memory. Because sometimes the operating system might decide to write memory pages to the swap space, to the swap device, even if there is free memory still available, because it wants to make free space for the file system cache, which is another component of an operating system that requires a lot of memory. In Linux, there is a Swappiness value as a kernel variable that can be tweaked to control how often and how early the operating system will write memory to disk, to the swap device. And a higher value there means that the memory is paged out earlier. The default value is 60 in a value range between 1 and 100, where 100 means page out memory as soon as possible, and 1 means don't page out until it is really necessary. Whenever possible, the bind 9 data, which is the zone files and its DNS cache in case of a DNS resolver, should not be paged out, because paging out and then paging in again that memory is really, really slow. And that is not what we want from a DNS server. So we can reduce the Swappiness parameter, and we can also restrict paging with the control group settings in systemd, and we will see that in a later chapter in this webinar. Also, if paging can't be restricted, the use of compressed RAM or ZRAM is a good alternative to a disk-based swap device. With ZRAM, there is a virtual swapping device in memory that, instead of writing memory pages to disk, will compress them with a very efficient and fast compression algorithm, and then stores the compressed pages in memory and freeing up conventional memory by doing that. Whenever application requests memory or return memory to the operating system, they make use of library functions such as malloc and free. Because the operating system and also the libraries that implement malloc and free don't know what kind of applications are running on the system, they need to be very generic. So they have to work reasonably well for applications that request just a few, but very, very large blocks of memory. And they also should work well with applications running many small blocks of memory, like a DNS server. And they also need to work well on single core machine, maybe embedded machines, and they must work on really large multi-core, multi-CPU machines. So in older bind versions, which is everything up to bind 9.16, or I think bind 9.16.24 that was, bind 9 implemented its own memory management, which ran on top of the operating system or library supported memory management. So bind was requesting larger blocks of memory and then doing micromanagement of these larger blocks internally with its own memory allocator that was built into bind. And that has been a common scheme for memory allocators 20 years ago, because the memory allocators that were coming with the operating systems weren't very, very sophisticated. And these simple allocators, they very often do not return memory to the operating system. Instead, if memory is being freed, they just kept the memory for later use. Memory can fragment, similar to file systems, because especially if smaller blocks of memory are allocated and then freed and allocated again and freed again, new free blocks might be too small for the new allocations, and that will create unused holes in the memory space. Holes where the memory allocator waits for later time to fill in these gaps with new allocations. And because of that, the application can consume more memory than it is really using. And in the worst case, that can be up to 50% more. Meaning that if you configure the bind 9 DNS cache of a DNS resolver to be 2 GB, bind might actually need more than these 2 GB of physical RAM to run the memory pattern it uses, because it fragments the memory, especially with a DNS resolver, which needs to allocate a high number of very small memory chunks for all the DNS resource records coming in, and then freeing these memories when the time to live expires on these resource records. That can create a highly fragmented memory space. And here we have memory fragmentation in a little graphic. We have the initial allocations. Here the different colors are different allocations in memory, and then 7 blocks of the allocation in the middle have been freed, and then the next allocation requested is for 8 blocks. And because the blocks always need to be continuous, now the 7 blocks are kept free and create a hole, and they will the hole will be there unless the memory allocators requires a new allocation that is smaller than 7 blocks or equals 7 blocks. We can tune the memory allocator, and there are many, many ways, but it's very important that you just don't tweak with the memory allocator and then just work on your gut feeling. If you do tuning on the system, it's good to have good measurement on what are the effects of the tuning. Is it really better? Is the memory usage optimized? Is it improving? And also, what is the impact of performance? Because speed is often a trade-off between the raw performance and the memory usage. So having an algorithm that uses more memory can sometimes be faster than an algorithm that is more memory conserving, which then might be slower. The default allocator being used on a Linux system is the malloc in the GNU libc library, and that is being used in bind 9.18 and also all the binds, if not told otherwise. And the GNU libc allocator works well for many application workloads, but it's not really optimized for a high number of small allocations, such as we see in the bind 9 DNS resolver. Because of that, the development team at ISC has tried different other allocators that are available. And one of them is Jmallock, which is coming from the FreeBSD project, but it's also available on Linux. And it's a standard package that you can install on Red Hat Linux or Debian or Ubuntu Linux. Starting with bind 9.18, bind will compile directly with that Jmallock allocator when it finds that allocator being installed on the system. And Jmallock shows better memory usage and better performance for bind 9 compared to the default, the standard GNU libc memory allocator. And we will see that we can use Jmallock also with older bind 9 versions as well, and might have better performance and less memory usage on older versions as well. So if we use bind 9.18 compiled for some bleeding edge Linux distributions like Fedora 37 or Debian Unstable or Arch Linux, we have Jmallock already as a dependency. So just installing the latest bind 9.18 on this operating systems will give us Jmallock. However, not many people run a bind server on bleeding edge Linux distributions. Most of the time, long-term supported Linux distributions are being used for a good reason. So another option would be to compile bind 9.18, and prior to compiling bind 9.18, to install the Jmallock development files, that is the header files. And when compiling bind 918 on a machine where the Jmallock header files are being installed, bind 9 will pick that up and will automatically configure itself to use the Jamalock allocator instead of the GNU libc allocator. If you don't want to compile bind 9 yourself, you could also use the binary packages for popular Linux distributions that are provided by ISC. And ISC has packages for CentOS, for Ubuntu, Fedora, and Debian. These packages have a more recent version of bind 9 than come with the operating system itself, and they have already support for Jmallock compiled in. And you can find information about the bind 9 packages on this link here in the ISC knowledge base. Here are the commands to install bind 9 from the ISC repositories with Jmallock on a CentOS 7 system. You first have to install epal release, because that gives you the DNF command, which is the more modern packet manager for Red Hat flavored Linuxes. Then we install DNF. Once we have DNF, we can install the copper subcommand, which enables the use of foreign repositories. Then we use DNF copper enable to enable the ISC/bind repository, and then we can install ISC-bind on our machine, and that will give us the latest 918 with Jmallock. If even that is not possible, then there is still a chance to use Jmallock by preloading Jmallock into memory before starting bind. And that works with older versions of bind 9, and it also works with bind 918 that has not been compiled with Jmallock. Preloading Jmallock doesn't give us all the benefits of linking with Jmallock in when bind is compiled, but it already gives us some benefits of the new memory allocator. If we preload a library into memory before the application is started, the functions that are defined in that library will overload all the functions that are defined in different libraries and in being used by that application. And in case of Jmallock, these are the malloc and free functions. Preloading is done by specifying an environment variable called ld_preload. On a Debian/Ubuntu system, we do that in the file etc/default named, and we just go into that file and we specify the ld_preload environment variable with the path, with the full path to the libjmalloc shared object file, which in case of Debian is userlib x64_86 64 Linux GNU libjmalloc SO2. Similar on Red Hat flavored operating systems, there the file is in etc/sysconfig named and it works the same, just that the path to the libjmalloc file is different. Once we have done that and restarted bind with systemd, so systemctl restart bind or restart named, we would like to verify that the preloading was actually successful. We can do that by looking at the memory mappings of the named process. Within the proc sudo file system, there is a maps file for every process running on the system. And that maps file lists all the named and anonymous memory mappings of that process. And because a library is a named mapping, we will find the name of the library in that memory mapping by grepping for the string alloc. And if we see libjmalloc being loaded into the process space of named, we can be certain that the new allocator, the Jmallock allocator, is being used. So with all this, we can optimize the allocator for a bind, but how can we measure memory consumption in a Unix or Linux system? A lot of people use TOP or similar tools. However, TOP shows numbers that are sometimes misleading because what's shown there as a memory usage is actually virtual memory. That is memory requested from the application towards the operating system, but not necessarily memory that is being in use by the application. A better command is atop, especially because atop shows more memory management details, but it also shows the growth or the shrinkage of virtual memory. So it shows the changes over time, and also it has the ability to log the data over time when you start atop as a background daemon, and then you can go back in time and see how bind has allocated memory and freed memory over time. So here in this example, we see the output of the top command for a running named process that uses 2.2 gigabyte of resident data, meaning real data, and it's using 2.7 gigabyte of virtual memory. So from the 2.7 of requested memory, only 2.2 gigabyte are really been in used. We also see the shared space memory that is being shared between multiple processors. Usually these are libraries that are loaded in memory and also being in use by other applications running on the system, which, for example, could be OpenSSL. Or we see the amount of swap space being used by this process. So how many memory pages have been written out to the swap file, and the size of the code. With atop, we see more. For example, we see the amount of data that is in the application binary itself, which is VS text, and the amount of space that is taken for the libraries, the space that is allocated for data, which is vdata, the stack, and with vgrow and rgrow, we see the growth or shrinkage of virtual memory and resident memory. An even more fine-grained and more accurate memory information we get with the Pmap command. The Pmap command maps all the memory pages that are loaded or are used in the process space of bind. And we see here the named memory pages and also the anonymous memory pages. We use Pmap and we specify the process ID of the running named process that we can get with the pgrep command. Pgrep named will give us the process ID, and we feed that into the Pmap. And here we see that the first blocks of memory are being taken by the named binary. Then we have some anonymous pages, and we have other libraries that are being loaded in, and we have a stack and more anonymous pages here. And at the bottom, we have the total amount of memory that is being used by this process. Another nice tool that will go through the data that is in the proc pseudo file system and will aggregate the memory allocation information for a process is called PSMem. That's written in Python, and you can install that via the Python packet manager pip. So pip install ps_mem will install this little Python script, and then we can apply PSMem to the process ID of the running named process, and it shows us the amount of data being currently used, which is private and is not shared with other processors, the amount of shared space, and the amount of real RAM being used and the swap being used. Another possibility to look into bind's memory usage is to use the bind9 statistics channel. The bind9 statistics channel is a way to view internal data from bind through a built-in web server in bind. If we want to use the statistics channel and we run bind on a machine with SE Linux enabled, for example, on a Red Hat Enterprise Linux, on a Fedora or CentOS, the SE Linux policy normally doesn't allow bind to open the port for the statistics channel. And we have to change the SE Linux policy to allow that. We do that with changing the Boolean variable named the TCP bind HTTP port on. And then we look at the permitted ports. And we see here the list of ports when we ask for SE manage port -L and then grep for HTTP port. And we either then need to pick one of these ports for the statistics channel, or we have to add a custom port to the HTTP port type. This is the configuration of a statistics channel. This is just listening on the loopback interface, and it allows connections from localhost. If you configure the statistics channel on a machine running in the internet, be careful that you don't open the statistics channel to the whole internet. Once that is configured and bind is being reloaded or restarted, we can test the statistics channel from the curl command by sending a request, HTTP request to the loopback interface, and then the configured port /JSON, and that will give us a JSON structure that gives all kinds of statistics information, and we are especially interested in the memory block that we see here. However, going through the memory information in the statistics channel can be quite cumbersome. So there is a little Python script provided by IC that will read the bind9 JSON statistics and will print out information about the memory allocations as seen from inside bind9. And that gives us the most detailed information on how bind is using memory. So we see data about the main program, the zone manager pool, which is all the loaded zone data, the authoritative data. We see the client manager that deals with client requests. We see the cache, and the cache is quite low here. This was an authoritative only server, the cache heap, and the databases. And in total, this machine uses 2.1 gigabyte of memory, and it also has allocated 2.1 gigabyte of memory. You find the memory JSON Python file as part of the bind9 memory explained blog post, and a direct link is here in the slides. Another interesting data point is the working set. The working set of an application is the total physical memory a process requires to work. And that might be less than the memory allocated by the application. Brendan Gregg, who is one of my heroes of system tuning, he wrote a blog post and little tools to measure and estimate the working set of an application. So you can find the tool on Brendan Gregg's GitHub repository, and that comes with a tool called wss.pl, which is written in Perl, and that goes through the memory allocations of a process and marks the pages as with a marker. And then it goes on there again and sees where the marker has changed. And that will tell the tool which pages have actually been used in the measurement time. So here in this example, we have measured named for 10 seconds. Out of the 2.2 gigabyte allocated by this bind instance, just 11 megabyte have been actively used, which means that at least for that 10-second time frame, the remaining memory was not active in use and could have been swapped out or could have been paged out. Of course, 10 seconds is not a good measurement time for such, but you could run this tool for an hour or two and then get a good idea on the amount of data that is really active within bind in your installation. So there are certain configuration settings in bind that can have an impact on the memory usage. And the first one, of course, is the cache size of a resolver. The option max cache size takes in percentage, which by default is 90%, or a fixed amount of memory. And that cache is being used for the record cache, for the positive and negative caching of resource records. That max cache size should never be set to 100%, because bind 9 needs other memory besides the cache to work. And if we set that option to 100%, then the cache alone will take all available memory in the system. And the remainder of bind doesn't have any memory to work with. So this can lead to the out-of-memory killer in the Linux kernel, or the systemd out-of-memory killer to immediately kill the bind process. In an ideal world, our cache should be large enough to store all the DNS records until their time to live expires, because cleanup of old cache entries based on the TTL expiring is less work for bind than freeing up still valid entries because the memory is being tight. However, depending on the hardware architecture, a too large cache can also result in real-world performance degradation. That you really have to measure. I can't tell you when that happened. I just have seen that it happens. It might have to do with cache coherence, that is the CPU caches and how they interact with the real memory. And the more DNS cache you configure, the more likely it is that the CPU caches don't have the data in the CPU cache that they need. I found that 2 gigabyte to 5 gigabyte cache size is a good starting point on a 64-bit architecture. That is the starting point. It's not that you configure 2 or 5 gigabyte and then call it a day. It might work, but best is to measure and increase the cache size and measure again and see what is the optimal setting for your operating system and your hardware configuration. We can tune the TTL cache times. We can create an upper bound for the TTLs with the max cache TTL and the max negative cache TTL. With that, we can prevent that DNS records are kept too long in our caches. So, for example, we could create an upper bound on the negative caching of 1 hour by setting the max negative cache TTL to 3,600 seconds. Newer versions of bind can also serve stale responses. And stale responses means that data that is in the cache that has expired, so the TTL has been counted down to 0, but it can't be refreshed because all the upstream authoritative servers are not responding anymore. And in this situation, bind will be able to still respond from the cache, even though the TTLs are expired. The current bind versions, which is 9.18 and below, do that for positive data, for positive DNS resource record, but also for the negative responses that have been cached, for the NX domain and no data responses. And that can be a lot of data that is being stored and kept in the caches. That will change in future versions of bind 9, and there's a ticket on that I listed here. Just be aware that if you configure stale DNS responses, that might increase the amount of cache data being used by the bind process. Also, newer versions of bind, 9.18 and up, will be able to synthesize negative responses from a DNSSEC signed zone using the NSEC and NSEC3 chain in the cache. So if bind has learned that certain names are valid in the zone and certain gaps between are not valid, it can synthesize the negative responses, the NX domains, directly from that data without doing a round trip to the authoritative server, which is the performance win and DDoS protection for the authoritative servers. But it also prevents that an extra NX domain entry is being stored in the resolver cache. The ability to synthesize negative responses was also available in previous versions of bind, but that implementation was not as optimized as 9.18, and it's currently not recommended to use that feature in older versions. If you run a split horizon DNS with multiple views, then you should know that each view by default will create its own cache. And each view will have a cache of max cache size. That is, if we keep it the default, then we have two caches of 90% of the hardware in the system, which results in 180% of overcommit. And that can create memory stress situations, even a situation where then the bind process is being killed by the out-of-memory daemon in the system. So if you run multiple views and you do that on a DNS resolver, not on a pure authoritative server, you should configure the size of the caches accordingly and make sure that the sum of the caches in each view don't exceed the amount of memory in your system. Or even better, maybe you can share the resolver cache between the different views, and you can do that with the attach cache option. And then multiple views can make use of a combined cache, and then that cache will only use memory once. Another option to save cache memory and an alternative for using the DNSSEC synthesize negative answers, the aggressive cache use, is to run a local root server copy on a resolver, meaning having an authoritative copy of the root zone on the resolver, because then the DNS resolver will be able to respond authoritatively for all the single label names. And especially in enterprise environments, we see quite a lot of these single label requests from either misconfigured machines or legacy Windows machines in the network. And that speeds up name resolution because the resolver doesn't need to send the request to the real root name servers. And also it saves memory because the negative response doesn't need to be cached in the system. So this is an option for DNS resolver that can't use the thin from DNSSEC setting. So bind 9.16 and older can use this. Another option is to use or to be authoritative for local and private zones. So if you use your private namespace, names that are not delegated in the internet DNS, then your DNS resolver should be authoritative for these zones. That will prevent leakage of internal information. It also speeds up the name resolution for these local and private names. And it prevents caching of negative responses that come from the internet routes for these private names. If you do that, don't forget the private IP address ranges for reverse resolution, the in-address RPAR and IP6.RPAR. And also for the resolver, if you use response policy zones, these response policy zones can be quite large. On one of my systems, the response policy zones take up more than 3 GB of data just for the response policy zones. And these are response policy zones that I subscribe from an external source. And these external sources, they can change. If the provider of the source finds a lot of new entries that are malicious, then an RPZ zone can all of a sudden grow in maybe 500 megabytes or even 1 gigabyte from one day to another. So you should have enough headroom in your DNS resolvers to accommodate this growth of the response policy zones. And if you rewrite responses with response policy zones, use the option qname wait recurse to no, because that will prevent normal recursion from happening, and also then preventing the caching of the requested names, because the response will be rewritten anyway. So it's not required that we first request the real name, store the real name in cache, and then not use that data anyway and rewrite the response to the client. So most configuration items go about the DNS resolvers, but we have some that we can use on an authoritative server. If we have views, if we have a split horizon authoritative DNS, then if the same zone, the exact same data should be seen in multiple views, we can use the InZone statement, and that will then use a zone within a view that is where the zone is being defined in another view, and it will only take up space once. Here in this example, we have a view internal, which defines the zone example.com just as a normal primary zone. And then we have the view external, and there we don't define the zone as a primary zone. Instead, we just define that this zone is in view internal. And so any request coming to the external view will just use the same zone data as the internal view. It's in view, sorry. I just see the request in the chat. It's a mistake here on the slide. The statement is in view, not in zone. The text on the top is wrong. So sometimes we want to restrict the memory usage of our bind server so that the bind server doesn't run into out-of-memory situations, or worse, that the bind server couldn't grow as large that other applications running on the same system, like the secure shell daemon, are then killed from the out-of-memory daemon. On Linux, we can use systemd with the control group feature to restrict resource usage. And one of the resources we can restrict is the memory usage. That can be configured in the services unit file. And if we want to do that, we have to first switch on memory accounting, and then we can configure memory high, memory max, and swap max. And I explain these settings on the next page. So first, memory accounting needs to be enabled for this feature to work. Then memory high specifies the throttling limit of memory usage for the process. meaning that this is not a hard limit. It's more than if the process already uses that much memory, the process are being slowed down and memory is taken away aggressively from these applications that reach the memory high. Memory max is a hard limit. If the process cannot comes to the memory max border, it cannot allocate more memory and the calls to malloc will fail. It might also result in the process to be killed from the out of memory daemon. Memory swap max defines the limit on swap usage of that processes in the unit. And for bind 9, we usually don't want any part of the bind process to be paged out to a swap file. So makes sense to configure memory swap max to 0. Once we have done that, we can control whether these limits are active by restarting the servers and then using systemctl status on the servers to see the memory line, which I highlight here, and it will give us information about the current memory usage, 2.2 gigabyte here. This process has a high limit of 3 gigabyte and a max limit of 4 gigabyte. Even though there's more memory in this system, bind will not be able to use more than 4 gigabyte on this system. And the maximum swap is 0 byte, meaning it will never swap out. And the available memory within its limit is 796.3 megabyte. So last chapter, and we are almost done with this webinar, about bind 9 memory in NUMA machines. NUMA means non-unified memory access, and it describes a computer architecture where the memory, the RAM, is connected differently to the CPU cores. And today, the AMD Ryzen Zen architecture is a popular non-unified memory architecture. So here we see a traditional UMA, that is unified memory access architecture, where all the memory is on the same memory bus and is connected to the same CPU. So it doesn't matter whether the CPU accesses data in memory 1 or 2 or 3 or 4 or 5, the performance is almost always the same. There's no difference between the different memory banks that we see here. In a NUMA architecture, we have different memory banks connected to different memory buses, which are then directly connected to CPU nodes having multiple cores. In this situation here, core 1 to 4 have direct access to MEM1 and MEM2. So accessing MEM1 and MEM2 from these 4 cores is faster than accessing memory in MEM3 or MEM4. It's still possible for the cores in CPU node 1 to access data in MEM3 or MEM4, but they need to go through CPU node 2, and that is an extra latency penalty going through that. If we have such a NUMA machine, a non-uniform memory access, we can optimize performance by restricting bind 9 to just use specific CPU cores and specific memory banks. For that, we have to know which memory banks are connected to which CPU cores, and the tool NumaStat will tell us statistics and also the information about the layout of the NUMA memory. And once we know that, we can use systemd units to bind the bind process to fix the bind process, to pin it to certain CPUs and to certain memory nodes. As we see here in this example, we have to enable CPU accounting, and then we can set the allowed CPUs and the CPU affinity to certain CPU cores. In this example here, it's core 0, 24, 48, 72. And then we use the memory nodes 5 to 8 and 12 to 14, which in this situation here, in this particular machine, might be directly connected to the CPU numbers shown here. This is highly dependent on your hardware architecture. So if you want to do that, first get familiar with NUMA architectures and the tools that show you how your memory layout is connected to the CPUs in your system. So sometimes to fully utilize a NUMA machine with many cores and many memory nodes, it might be necessary to run multiple bind9 instances, so multiple bind9 processes, each on its own NUMA node and memory nodes, then having one large bind9 process running. There is a feature in bind9 on Linux and FreeBSD that will enable bind to use an already used port 53, and to have multiple processes listening on the same port. And that is the option reuse port true. If you configure that, you can start bind multiple times, and the operating system will distribute incoming queries on port 53 towards the different bind9 instances. So it's like a small DNS load balancer built into the Linux kernel that dispatches the incoming requests to multiple bind9 processes, and each bind9 process is then running on its own NUMA configuration, having its own local CPU cores and its own local memory. So as always, we have a number of resources here for you to read about the different allocators and recommendations for books and information about how to tune a Linux system. Even more resources, performance data from the ISC development team. And then upcoming webinars. There will be more webinars next year. And if you have ideas what we should have as topics in the webinars, please let us know, write an email or write in the chat today. And we will go through these ideas and take inspiration and prepare the webinars accordingly next year. And this brings us to the question and answers.